We are acquainted with the fact that gases exert pressure. Gaseous pressure drives this plane forward, and a difference in air pressure between the bottom and top of the wing keeps the plane aloft. Of course, airplanes are not the only massive objects which remain aloft in the atmosphere. Clouds may also weigh many tons. How can the water droplets which make up the cloud remain aloft? Let us take a closer look at the cloud. Here is a portion of a cloud viewed through a microscope. The random motion you are watching is called Brownian motion, after the British scientist who first studied it. Something must be jostling these droplets. Here is an object jostling about in much the same way. Turning up the light shows this object is being hit randomly by many small marbles, moving rapidly in all directions. Just as these marbles bombard the large object, pushing it this way and that as more marbles hit first one side then the other, so the random collisions with air molecules account for the erratic motion of cloud droplets. Since the force of these collisions with the molecules is large compared to the pull of gravity on a drop, the drops do not fall. Pressure in general can be interpreted in terms of random molecular collisions, and pressure differences, as in the airplane, can arise when more molecules per second strike one surface of an object than strike the other surface. We can study the behavior of gases in a pictorial fashion in this machine. Marbles are placed in it, and a vibrating disc at the bottom drives them in a vertical direction. They can strike on the bottom of this piston, which is attached to a gauge. When the machine is operating with only a few spheres in it, we notice that the gauge swings back and forth unsteadily. This is the result of the small number of random collisions per unit of time. With more marbles in the machine, the number of collisions per unit of time should be greater. The gauge reading should be higher. The pressure is higher. Now let's try a quantitative experiment with a real gas. We shall use this equipment. These bulbs contain carbon dioxide gas. They are connected through this stopcock, which is sealed off from the atmosphere. With the stopcock open, the pressure in the two containers is the same, half an atmosphere. Since so many molecules are striking each gauge per second, the pressure readings are steady. Now, Avogadro's law tells us that at the same temperature and pressure, equal volumes of gas contain equal numbers of molecules. Thus, with these equal volumes at the same temperature and the same pressure, we have as many molecules of carbon dioxide in here as in here. Now, what will happen to the pressure if we transfer all of the molecules into one bulb? This bulb, for example, thus doubling the number of molecules in it. Well, here's one way to do it. We close the stopcock first, then take some liquid nitrogen and place it around the tip of the bulb. The pressure in this bulb drops. Carbon dioxide is solidifying on the cold inner surface. Since the molecules no longer bounce around, the pressure drops to zero. Now let's open the stopcock. The molecules that were in here move into here, and they solidify. The pressure in the whole system drops to zero. All the molecules are now in this bulb. I'll close the stopcock, remove the liquid nitrogen, and replace it with water at room temperature. The solid will now vaporize into gas, and the pressure rises. All right, the solid has all evaporated and come back to room temperature. The pressure is now 1 atmosphere, twice what it was when we had half as many molecules in this bulb. By opening the stopcock, we can check this relationship between pressure and number of molecules. The pressure drops to half an atmosphere as the molecules redistribute equally between the two bulbs. These and many other experiments show us that pressure is caused by molecular collisions. Changing the number of molecular collisions changes the pressure. We have studied the effect on pressure of changing the number of molecules in a fixed volume. Let's now study the effect of temperature on pressure. In order to study the effect of temperature, we shall need a substance that remains a gas at low temperatures. From this table, we can see that helium boils at minus 269 degrees centigrade. Let's use it. It should not condense as did our carbon dioxide earlier. We have placed helium in this flask at 1 atmosphere pressure. Let's immerse it in boiling water. The volume and the number of molecules remain constant, but the pressure changes. The pressure is 1.24 atmospheres at 100 degrees centigrade. Let's put the bulb in melting ice now. And while it sits, record the data from the boiling water. At 100 degrees centigrade, we get a point here. Our gas was helium. Now let's record the data from the melting ice. The pressure in melting ice is 0.93 atmospheres. Let's take the container out and place it in dry ice at a temperature of minus 79 degrees centigrade. And again, while it sits, record our data. At 0 degrees, we get a point here. Now let's check the dry ice. The pressure at minus 79 degrees is 0.67 atmospheres. Now let's try liquid nitrogen at minus 196 degrees. For dry ice, we got a point at 0.67 atmospheres. The pressure at minus 196 degrees centigrade is 0.27 atmospheres. And notice, the helium is all gaseous. Thus, the data for liquid nitrogen give us a point here at 0.27 atmospheres. Now let's try passing a straight line through these points. We see that within experimental error, the line goes through all the points. Furthermore, were we to repeat the experiment with other gases starting at the same pressure, we would find that all gases give data which fit on this line. Perhaps you would like to use these data to get a value for absolute zero. However, for the purpose of this film, all we need to realize is that a fixed volume of gas, which contains a constant number of molecules, gives a different pressure when we vary the temperature. Thus, any variation in the absolute temperature changes the pressure proportionately. Now, what does this mean in terms of molecular collisions? Perhaps our marble machine will give us an interpretation. We've already seen that the pressure changes when the number of marbles changes. But note, changing the velocity also changes the pressure. Could it be that the effect of temperature on the pressure of a gas is a result of molecular velocity varying with temperature? In fact, since the pressures of all gases behave alike at varying temperature, perhaps the velocity of all gases is the same at any given temperature. We can explore this possibility experimentally. Here we have a simple apparatus which will give us further information. The 4 tubes have been filled with carbon dioxide gas. The pressure is kept constant by this tall column of liquid. With this yoke, I can turn all of the stopcocks simultaneously. When the stopcocks are opened, the molecules of trapped gas can strike these foils. In the center of each foil is a tiny hole, so small as to be almost invisible to the naked eye. When the molecules strike the hole, they escape, and the volume of trapped gas decreases. The rate of escape can be determined by the rate at which the liquid rises in the calibrated tubes. Since conditions are the same in each tube, the escape rate should be the same, and the liquid level should rise at the same rate in all the tubes if all the tiny holes are the same size. Well, all the levels have risen the same amount. The holes are indeed the same size. Now let's repeat the experiment using 4 different gases. The tubes are now filled with equal pressures of hydrogen, oxygen, carbon dioxide, and sulfur hexafluoride. We'll start the escape simultaneously and measure the volumes which escape. But look, the liquid rises at different rates. We'll stop the experiment when 1 unit of the slowest gas has escaped. Well, reading the bottom of the meniscus, 1 volume of sulfur hexafluoride has escaped, and 1.9 of carbon dioxide. 1.0, 1.9. For oxygen, 2.3, and for hydrogen, 8.7. 2.3, 8.7. Are the rates of escapes related to the molecular velocities of these gases? Let's review the experiment. The pressures in each tube were the same, so were the temperatures. Thus, according to Avogadro's law, each tube originally contained the same number of molecules. Yet different numbers struck the tiny holes and escaped from each tube. Since more hydrogen molecules escaped, they must have struck and gone through the hole more rapidly. Their molecular velocities must have been higher than those of the other gases. In fact, since over 8 times as many hydrogen molecules escaped as sulfur hexafluoride, the hydrogen velocity must be over 8 times greater than that of sulfur hexafluoride. In the same way, the molecular velocity of carbon dioxide is 1.9 times that of sulfur hexafluoride. and the molecular velocity of oxygen 2.3 times that of sulfur hexafluoride. Let's search for regularities among these velocities, some factor which correlates with them. For example, we notice that hydrogen and oxygen are diatomic, carbon dioxide triatomic, and sulfur hexafluoride contains 7 atoms per molecule. Yet these do not correlate well with velocities, as we can see from looking at the fact that hydrogen and oxygen each contain 2 atoms per molecule, but differ greatly in velocity. In the same way, shape and size do not correlate well with velocities. Hydrogen and oxygen have very similar shapes and sizes, but they differ greatly in velocities. On the other hand, carbon dioxide and sulfur hexafluoride are not greatly different in velocity, but there is a considerable difference in their shape and size. What about molecular weights? The molecular weights are 2, 32, 44, and 146. As the molecular weights increase, the molecular velocities decrease. Do we have a regularity here? We have plotted molecular weight versus velocity in this book and have obtained a smooth curve on which the points lie. In fact, data for all gases would lie on this same curve at this temperature. There is indeed a relationship between molecular velocity and molecular weight. Further examination of these data would show that they fit the equation m times v squared equals c. Molecular weight times molecular velocity squared equals a constant at constant temperature. Perhaps our marble machine will clarify this further. It has been modified to represent 2 escape tubes. There is a hole in the side which can be opened so the marbles can escape. We have several hundred marbles in each tube, but each of these marbles weighs much more than each of these. So we have the same volume containing the same number of marbles, but the masses are different. Now let's make the pressures the same. With the pressures the same, and the volumes and numbers of marbles the same, we have, according to Avogadro's law, the same effective temperature. Let's start the escape. More of the lighter marbles have escaped than the heavy marbles. So we have a model which interprets the fact that light molecular weight gases escape faster than heavier molecular weight gases. The lighter molecules travel faster, have a higher molecular velocity than the heavier gases at the same temperature. Now what about changing the temperature? We collected our data at room temperature. If we repeat the escape experiment at different temperatures, we obtain these relative velocities. Notice that as the temperature rises, the molecular velocities always rise. Now from separate experiments, we know that the molecular velocity of oxygen is about 48,000 centimeters per second at room temperature. Using this fact and our experimental data, we can calculate actual values for mv squared for each gas. Notice that at each temperature, the values are constant with an experimental error. The average value here is 4.6, here 6.8, and here 8.6, all times 10 to the 10th. If we divide these average values of mv squared by the corresponding value of the absolute temperature, the resulting values of mv squared over T are almost constant. Thus the relationship between molecular weight, molecular velocity, and absolute temperature is given by the equation mv squared equals a constant times the absolute temperature. Thus our molecular model does give us a picture of pressure in terms of molecular collisions. The number of collisions depends on the number of molecules per unit of volume and their molecular velocity. Lowering the temperature decreases the molecular velocity, which decreases the pressure. At any given temperature, lighter molecules have a higher velocity. Finally, the relationship between molecular mass, molecular velocity, and absolute temperature is given by this expression. Any change in the absolute temperature causes a change in the molecular velocity.